which actually I was tempted to use, but since the whole Denmark uses this one. Okay, so starting. Good. So let's recall a few notions. So so there's a basic topological notion, a subset G in say complex numbers. Although I'm not using anything about complex numbers. I'm not using even distance, so it's not about metric. It's about topology, so about the notion of open set. So so G is called compact if for any covering of G. So what it means is that G sits inside the union of probably infinitely many where alpha is enumerated by some set S, and with these are open in C. There exist finitely many indexes that such that G sits actually inside this finite union. In words, any open covering has a finite subcovering. So I think you should have met this before. I'll write a reformulation which will be the one I'll use. So notice that in this formulation I'm not even using the notion of disk or distance or absolute value or anything. It's purely topological. But an equivalent definition is like this. So equivalent definition. G is compact if for any covering of G by open disks, and again indexes can be any, some points. So let's say that there are some points about K of A S R A alpha R A alpha. So union of open disks of course of positive radii. There exist finitely many alpha 1, alpha n. G sits in the union of these. So looking at these two, you see that the difference is not great because any open set is a union of open disks. So at least in one direction it's clear that there one implies the other, but you can go backwards as well. So main theorem about compact sets. Let G in complex numbers be closed and bounded. So closed in metric sense and bounded also in metric sense. then G is compact. You can compare this to something you probably know from real analysis. The interval is compact. You should know this, right? So, yeah. Now, definition. So the goal was, as you remember, to weaken the notion of convergence. So there are two notions, and they will turn out to be equivalent. So definition. Local uniform convergence. So we have a sequence of functions. So we have G open in complex numbers, and Fn is sequence of functions on G, and also F is a function on G. So we say that Fn converges to F locally uniformly if there exists, so for any point A in G, there exists a closed disk, K-A-R, inside G, on this disk, Fn converges to F uniformly. Sorry, there were more chalk I did here. Converges to F uniformly on this closed disk. Okay, so of course this is so a priori this is weaker than Fn converges to F uniformly on the whole G. Great. Now there'll be another notion. So definition prime. In the same situation, so Fn and F are functions of G. Fn converges to F uniformly on contacts. If indeed any K in G compact, Fn restricted to K converges to F restricted to K. So before we continue, let's prove that these two notions are equivalent. So maybe let me introduce short notation. this thing is called uniform and compact. And this thing is locally uniform. So again, this is very standard, but let me still prove it. So yeah. Theorem. We have this sequence and this function on G. Then local uniform convergence is equivalent to convergence, uniform convergence on compact. Proof. So in this direction, it's clear. Because any closed disk is compact. So it's closed and bounded. So if we have uniform convergence on compact, in particular, we'll have uniform convergence on any closed disk. So this is not interesting. The interesting direction is this one. So we have local uniform convergence, and we want to prove uniform convergence on compact. So let K in G be a compact subset. Well, so for any point A in G and any so there exists this closed disk with the radius, of course, depending on the point in G, such that Fn converges to F uniformly on the disk. Well, of course, these disks totally cover G, in particular K. So K sits inside the union over all points in G, huge union of these disks. But being compact, there exists finitely many points, A1, AN, such that K actually sits inside finite union. K A1 R A1 K AN R AN. And I can even put here closures. Nothing will change. I just made this subset bigger. So it's a finite union, and uniform convergence, I mean, you can prove it by definition on this epsilon delta language, but uniform convergence definitely has this property that if a sequence converges uniformly on one subset and on another subset, then it converges uniformly on the union. So uniform convergence respects finite unions of subsets. So Fn converges to F uniformly on each K, A, I, R, A, I, implies that Fn converges to F also uniformly on the union of these. It's a finite union. I mean, uniform convergence means that you can, for every epsilon, you can choose a number starting from which the absolute value of the difference will be less than epsilon. You choose these numbers for each of them, and then you take the maximum of them. And starting from there, the difference will be less than epsilon everywhere. So it's this on the union, but then also we probably didn't state it explicitly, but uniform convergence also has this property that, so when I put a mark, Fn converges to F uniformly on a set A implies that Fn converges to F uniformly on any subset, on any B subset in A. So in particular, Fn converges to F uniformly on K, which is a subset in this. Good. So I proved it. Now we pass to what we were actually aiming. Theorem. So far it was like elementary analysis, not using anything about complex numbers. But now finally G is a domain in C, and we have a sequence Fn, a sequence of functions G to C. Each of them is a holomorphic. And Fn, the sequence converges to F locally uniformly on G. Then F is also holomorphic. And the sequence of derivatives converges to the derivative of the limit locally uniformly on G. So the form in which we'll use it is like this. So corollary. So again, we have a sequence of functions, and they're holomorphic. And then S of Z, which is some, so assume that this sum converges again locally uniformly. On G. And then, well, what we stated here, S is holomorphic on G, and S prime is sum of Fn prime. So it's clear how corollary follows from the theorem. You need to consider the sequence of partial sums, and that's exactly what happens here. So let me even put this on the blackboard. Theorem implies corollary. So I'll prove the theorem in a second. I'll just comment it first. So take Sn leave Sk. So partial sums. And then for this sequence of holomorphic functions converges to S locally uniformly. This is the what I meant by sum of series. Then apply the theorem. Let me make another remark before I prove the theorem. So the theorem generalizes something we saw before. So remember that if we have power series and this sum is called S on Z, converges absolutely on K0 If you think what it means, it in particular means that it converges locally uniformly. And we already know that, well, each term, of course, is holomorphic, it's just a monomial. So what we know is that S is holomorphic on this K0I. And S prime is given by series. Which is derivative of each term, of course. So it's just emphasizing that the result we plan to prove is generalization of this. Good. So now let's prove the theorem. So proof of the theorem. So we choose a point and a closed disk around this point inside G. So Fn converges to F uniformly on AR closed. Oh. So in particular, as we know, uniform convergence preserves continuity. So Fn are holomorphic, and then Fn is continuous, and then the limit, which is F, is continuous on R. Well, we're allowed to integrate. So let's take any solid triangle inside, so it's a small triangle. So Fn each I hope they would be rhythmic enough so so each Fn is holomorphic on this. Then the integral over the boundary is 0. On the other hand, we remember that we know for uniform convergence the integral over any closed curve, in particular over this boundary of the limit of Fn, which is f, is limit of integral over the same curve given by the boundary of the triangle of Fn. But this is 0. It's limit of zeros. So it's 0. So we get that for any such triangle like this, the integral over the boundary of f is 0. Now apply one of the versions of Cauchy integral theorem. And we get that we apply integral theorem. We get that the limit f is holomorphic in each K, A, R. But it's a local condition, it's a condition around every point. So, so thus, the limit of Fn, which is f, is holomorphic in the whole G. Now let's estimate so we want to compare the derivative of the limit and limit of derivatives. At every point. And that's why we use Cauchy integral formula. So we'll estimate the absolute value of the difference. So let's write this difference. So we'll write Fn prime of Z naught minus F prime of Z naught. And for both of them, we use Cauchy integral formula. So this is 1 over 2 pi I integral over d a r f of z minus z naught dz minus 1 over 2 pi I integral d a r f of z fn of z. Here is f of z. Squared, sorry. dz. So this is okay, so then we can put absolute value everywhere. Then we need estimates. So first of all, so since we're choosing our disks to be small, we can put Z naught even closer to the center of the disk. So we have this disk around A, and let's say that the point Z naught is even closer, so it's somewhere here. Okay. So then we can use the estimates. So I mean by the well-known estimate. So there'll be, so this is less or equal, so 1 over 2 pi. Length of the decay. Length of this decay AR times the maximum, the supremum of absolute value of Fn of Z minus f of Z divided by Z minus Z naught squared. So now let's see. By choosing, by uniform convergence, we can choose numbers so that this thing would be very, very small. So this, for n big enough, is less than epsilon. Now, so what we have here is, of course, the length of this circle. So this will be 2 pi r. Now, the estimate for 1 over z minus z naught squared. So z is a point on the circle. And z naught, as we decided, is inside the smaller circle. So the distance is greater or equal than radius over 2. This is my choice of the smaller circle. So then this is less or equal than 1 over radius over 2 squared. So if we combine this with that, we'll get we obtain 2 pi over 2 pi r by r squared and times 4 and times epsilon. So this is 4 over r epsilon, and epsilon was chosen uniformly, so for say any n greater than n naught, and any point z naught in k a r over 2. Well, this means that this n prime tends to f prime locally uniformly. Okay, so this is the end of the proof. And yeah, did I want to say anything else? Maybe we'll stop here. So the next statement is about the integral with parameter, and in a way I announced it as well, but I think that the proof should be put on the blackboard in detail next time. So let's stop here.